Hello viewers, welcome back to the lectures on stability of slopes. Today it is our 6th lecture. In our previous lectures we have already discussed the infinite slopes. In these slopes we assume the failure surface to be parallel to the ground surface, and we had considered many cases of the drainage conditions. Then we started with the finite slopes. Finite slopes are smaller in areal extent and generally they are man-made structure. There we discussed the Kuhlmann's method. Then we have already discussed planar failure, and then we started discussing about the circular failure, where the failure surface is taken circular. This was the case of a rotational slide. Here it is an embankment, and this is the failure surface which we have discussed last time. And in 2D this surface is circular, in 3D it is cylindrical surface. Perpendicular to the plane of paper we are taking 1 unit dimension. The general term is rotational failure or rotational slide, and we also discussed different types, subcategories. These were slope failure, toe failure and base failure. Then we discussed about the types of the stability analysis procedures. The first category is of those methods where the mass of the soil above the surface of sliding is taken as a whole, as a unit. The entire body is considered as a free body and its equilibrium is considered for analysis. In the second method, which is called as method of slices, the mass is divided into number of vertical parallel slices. So, we had started discussions on the first method, mass procedure. In mass procedure, we had taken the first case. It was homogeneous clay under undrained condition. The slope was having clay which is assumed to be fully saturated, that means phi u was 0, soil was assumed to be homogeneous, Cu was same at all the points on the failure surface, and the potential failure surface was assumed to be circular. The method of analysis included finding out the moment which are trying to rotate this slide. This is the example here. So, we took this circular surface and then here it is the weight. Its lever arm is L0. This is the center of the circle. This circle we have taken arbitrarily as the first trial circle we have taken. This is the radius. So, we find out the weight of this wedge and the moment which this weight is trying to generate. And this moment is being registered by the cohesive forces which are acting all along the periphery of this arc. So, if Cm is the cohesion, then you can find out the cohesive forces and their moments. So, Cm into the length of arc into radius, that gives you the resisting moment. And for equilibrium case, when the limit equilibrium condition is satisfied, these two moments are taken equal, means the resisting moment and the driving moments, they are taken equal, and from there you can find out what is the value which is required for the cohesion. So, this much value of the cohesion is required to keep it in equilibrium. So, this is mobilized cohesion. So, once we get that Cm, factor of safety can easily be found out by dividing Cu by Cm. Cu is the available strength, available undrained shear strength. So, Cu upon Cm, this is the mobilized value. So, Fs, factor of safety, is Cu upon Cm. So, this is what we had discussed last time, and I was discussing about the graphical solutions, because now what we have to do is, after taking one circle and doing lot of calculation, we have to take another trial circle, another center, and the same procedure has to be repeated number of times, and then we have to find out that circle which is having minimum factor of safety. So, the graphical solutions are very easy in these cases. So, here it has been produced, the graphical charts are available. So, on the x axis here you can see it is slope angle beta, and on y axis these are two parameters alpha and theta. Please refer this figure. Theta is this angle 2 theta, 2 theta is the angle subtended by the arc here, and alpha is this angle which the base, this particular line, it makes with the horizontal. So, the method becomes very simple. This is the case of the toe failure. What we have to do is, corresponding to the given beta value, we have to read alpha and theta. Say for example, if I take alpha is equal to 55 degrees somewhere here, then corresponding to that I will read here alpha will be somewhere more than 30, and then also I will read here theta, this is almost very near to 40, somewhat less than 40. Once you get this theta and alpha, now you can very easily draw this triangle. You draw a line at an angle alpha, get point B, and then this angle is 2 theta, you can very easily get this angle, and then you can draw this triangle and get the center, and then rest of the analysis can be done very easily. If it is a case of the base failure, when the circle is passing through the base, then what we do is, the center of the circle has to lie on a line which is drawn from midpoint M of the slope, and this line is vertical. It is because the circle has to pass in this manner. This is the firm base, it is a base failure. So, circle is tangential to the base, and base we are assuming to be horizontal. So, the circle has the center has to lie here. This angle, this line and the horizontal line, they should be perpendicular to each other. So, here the O is the center of the circle, and these are the parameters. H is the height of the slope, and the base is situated at ND times H depth below this level. So, ND is a parameter. Another parameter here in this analysis, in this graphical solution, is Nx here. So, x is Nx into H. This gives you the point where this circular surface intersects the ground. The distance of this point from toe is Nx into H. So, these are the parameters Nx, Nd, and then one can, the graphical solutions are available here for any value of beta. For these are the beta values here on x axis, on y axis these are Nd values, and these are the different curves for different Nx values. So, for any beta value, say for example 30 degree, and for any Nd value, say for example 2. So, Nd is equal to 2, beta is equal to 30, here it is the point. So, this is roughly, this curve is Nx is equal to 1, this curve is Nx equal to 2. So, you can interpolate in between them what is Nx, and then you can find out, once Nx is known, you can find out the point where the circle is touching this point, how far away from the toe it is touching the ground, and then you can complete this circle. Let us take an example. This is an example of toe failure. This is the general diagram. H is the height, beta is the slope angle, and these are the data. Given for a cut slope in saturated clay, the height of the slope is 7.5 meter, and the saturated unit weight is 15.7 kilonewton per meter cube. Cu is 24 kPa, slope angle beta is 56 degree and we are asked to find out the factor of safety. Now, I told you in the last class that for beta more than 53 degree, the slope in this case of in this case condition will always be a toe failure. So, here beta is more than 53, beta is 56. So, it is more than 53. So, it is a toe failure. So, let us use the graphical solution for toe failure. So, for 56, so this is 50, here it is 60. So, somewhere here the 56 will be there, and corresponding to that the alpha value roughly comes out to be 33, and here this is theta, it comes out roughly about 38. So, now you know these two angles, you can complete the diagram. You can make it, you can solve this problem graphically also, or you can solve it analytically. So, this angle is known to you, alpha is known to you, 2 theta is known to you. Once 2 theta is known to you, you can find out this angle. So, and then rest of the things have to be done. So, here A, B, this comes out to be h into cosec of alpha, this comes out to be 13.77 meter, and the radius in this particular case comes out to be 11.19 meter. I am not showing the rest of the calculations, they are simple. You can do the geometrical you can use the geometry, and then you can find out the weight and Cg of the mass above the sliding surface. Then you can find out the moment of the weight, as I discussed. This moment will be weight into its Cg from the center of the circle. In this case, I got this value. Then length of circular arc also you can get very easily, and then you can get the mobilized cohesion, the cohesion which is required to keep this slope in equilibrium. So, Cm comes out to be 32.82 kPa. So, this is the value of Cm which is required, and the available value given in the problem was 24 kPa. So, you can see here available value is 24, we required around 32.82, factor of safety is 0.73. So, it is not safe, we need more. For the stability of the slope, higher value is required and the available strength is 24. So, factor of safety is 0.73. Now, there is another way of solving these problems. This problem was solved analytically by Felenius and Taylor, and for critical circles they have given the solution in terms of the stability number. The stability number is defined as Ns is equal to Ca upon gamma h. This is we have already defined it. So, for case of the mobilized cohesion, Ns will be equal to Cm upon gamma h, and for the case of the critical height. So, when critical height means maximum height, if you want to calculate what is the maximum permissible height. So, factor of safety will be equal to 1, Cu and Cm will become equal. So, in that case if you take it on this side, so critical height will be equal to Cu upon gamma into Ns. So, this Ns has been given. The values of stability number Ns for various slope angles beta are given in the figure. I will show that figure to you. This figure is valid, this chart is valid for slopes of saturated clay and applicable to only undrained condition. This is important point. This particular chart is for this specific condition. One more thing here I would like to mention is that sometimes in the literature you will find another term, stability factor. So, this stability factor is nothing but it is the reciprocal of the stability number. So, we will use stability factor also in future. Here it is the chart of the stability number. On the x axis the slope angle is given in degrees, and on y axis it is stability number. So, it is 0.1, 0.2, 0.3 value, and you can see from around 53, beta equal to 53 and more than 53, you have only one line. This means this is for the toe failure. So, this solid line is for toe failure. For steeper slopes, when beta is more than 53, only the toe failure occurs. If it is less than 53, then this can be a base failure or slope failure. So, the charts are available for both the cases. If it is a midpoint circle means it is a base failure. In case of the base failure, the critical circle is called as midpoint circle. And slope failure, if it is the circle is passing above the toe, that is slope failure. So, for that different lines are available. So, what we have to do is for corresponding value of beta, say for example, beta is 60 degree. So, if you take the intersection here, straightway you get the value of stability number, and that stability number is related with C, gamma and H. So, you can have a relationship between C, gamma, H. You can have a parametric analysis. If gamma, H something is given, you can find out C. If C is given, you can find out H, and any sort of analysis can be done. To use the stability number for a slope beta more than 53 degree, the critical circle is always a toe circle. That is what I told you just now. And if beta is less than 53, then the critical circle may be a toe circle, it may be a slope failure, or it may be a base circle, depending on the location of the firm base under the slope. The depth function d is defined as, so here you can see that there is a little bit difference in the parameters of this graphical solution. Please note down here what is d. You have to be cautious when you use these results. So, d here is defined as vertical distance from top of the slope to the firm base, and it is divided by height of the slope. So, it is the ratio of the depth of the firm base and the height of slope, that is d. For base failure, the critical circle is called midpoint circle. This I told you, for when it is passing through the base, the critical circle will be called as midpoint. It may be obtained with the help of the figure, which the figure will be given subsequently. I will just show it to you. Last point is that maximum possible value of the stability number for failure as a midpoint circle is 0.81. Here this is the chart which can be used to find out the location of the midpoint circle. I defined the parameter d there. D was the ratio of the depth of the firm base to the height of the slope. So, d is here, and another parameter n is here, and for different beta values these are the curves. So, for example, if beta is equal to 10 and d is equal to, let us say, 3, then for 10 you can find out what is n. This is the this figure gives you again the definitions. N is n which I defined there. N is a coefficient which you have to multiply with h to get this distance, the distance where this circle touches the ground. So, a relationship between n, d and beta is available. So, if you know the depth of the base and if you know the h value, you can very easily find out. So, to find out this, you have to use this graph. So, for the given n value, for given beta value, you can have d or vice versa. Let us solve an example here. It is given that a cut slope in saturated clay makes an angle of 60 degree with the horizontal. The properties of the clay are Cu is given as 25 kPa, kPa means kilonewton per meter square, gamma is 16 kilonewton per meter cube. We have to determine the maximum depth to which the cut could be made, the critical depth, and secondly depth of the cut if we need to have a factor of safety of 2. We will solve this problem by using the stability number. The stability number is defined as Ns is equal to Cm upon gamma into h, and when the factor of safety is 1, Cm will be equal to Cu. So, Ns is equal to Cu upon gamma into h, here will be critical, h critical. So, put these values, Cu is 25, gamma is 15, h is unknown. So, this is Ns. Now, from this chart you can see the value of the stability number corresponding to the given beta values. Beta is given as 60 degree. So, for 60 degree you can see from here this is 50, 60, and as I go up this is the point of intersection, and from here this is less than 0.2, little less than 0.2. So, here you can interpolate it, and I got this value as 0.195. Put this 0.195 in the previous equation. So, 0.195 will be equal to C upon gamma h, and that gives you h is equal to 8.01 meter. So, it is very convenient to use these charts. Now, for the second part of the problem, it was told that the factor of safety needed is 2. So, that means now you can find out Cm is equal to Cu divided by factor of safety. Factor of safety is nothing but a ratio of available strength divided by the mobilized strength. So, from here I get Cm value, and Cm value comes out to be 12.5 kPa. So, mobilized now is 12.5. The rest of the analysis is same. The stability number depends on beta, it is same here 0.195, and C is 12.5, gamma is 15, h is the new height which is corresponding to 2 factor of safety, and by solving this equation you will be getting the height. So, this is the safe height for safe factor of safety. Let us have another example. This is a cut slope. Now, the angle is small, angle is beta is 40 degree only. This was excavated in a saturated clay. Slope failure occurred when the cut reached a depth of 6 meter. Now, this is given that when it was 6 meter of the depth was reached, the failure took place, means the limiting condition was reached. Hard rock stratum lies at a depth of 9 meter. Now, this is given here, the firm base is available at a depth of 9 meter. Given gamma saturated is 17, determine undrained cohesion of the clay. Now, here it is the property which we are trying to determine using the back analysis. Secondly, the distance at which the sliding surface intersected the bottom of the excavation. Now, it is given that limiting height now is 6 meter, gamma is 17, and depth of the hard stratum is 9. Now, if you remember, the nomenclature which we had used was that d into h is the depth of the hard stratum. So, d into h is equal to 9. So, this parameter d of the chart comes out to be 9 upon 6, that is 1.5. Now, from the figure which I was discussing, where d and n and the stability numbers were available. So, for beta equal to 40 degree, and now I use the base failure, the curve, the chart for the base failure is used, and you will be getting Ns is equal to 0.175. Also, factor of safety is 1 here because it was the limiting case. So, Cu is equal to Cm. So, the expression of the stability number will be Ns is equal to Cu upon gamma h, So, 0.175 is equal to Cu upon 17 into 6, and that gives you the value of Cu as 17.85 kPa. This is the chart which I had used here. For beta equal to 40 degree, you can check for base failure. So, beta equal to 40 degrees. So, here it is 0, 10, 20, 30, 40. I have to go along with this direction, and here you have to use the base circle. Base circle means midpoint circle here. So, this is the these are the charts for different d values, and d here it is given as we have calculated as 1.5. So, this is d is equal to 4 and 1.5 is here, this one 4, 2, 1.5, 1.2. So, corresponding to 1.5 we get somewhere here. So, somewhere here, and that value one can easily interpolate. That value was 1.175. So, once NS is available, now this expression is simple to use and you get value of Cu. Now, in the second part of the question, we have been asked to find out the point where the failure circle is meeting the ground. So, this is the chart. I have already shown it. On the x axis you have n, on y axis you have d. So, now in this particular case d is 1.5 and beta equal to 40. So, d equal to 1.5 is somewhere here. So, corresponding to this, and beta equal to 40. So, 40 is this circle. So, somewhere here you get the point, and we get n roughly about 0.9. So, distance NH as per this graphical solution comes out to be 0.9, that is n, into h is 6, that is 5.4 meter. So, you get the final answer where the circle touches the ground. So, that was the case of the saturated clay. Let me now go to the next case. It is again a saturated clay, but we are now taking into account the earthquake forces also. So, here it is the mass procedure. Once again it is mass procedure, we are not dividing the mass into the slices. So, it is mass procedure for stability of saturated clay slope with earthquake forces. So, here it is the slope, the B point is the toe of the slope, and here this is a trial circle we have taken, center is O, and the CG is CG of the mass above this failure surface, entire mass is here. Weight W is acting in downward direction at the CG. The additional component which we are going to get in this case is the force due to earthquake, and that force is taken as the weight of this wedge multiplied by a coefficient Kh. Kh is the ratio of the acceleration due to earthquake divided by the acceleration due to gravity. So, this Kh multiplied by W, that gives you the force which acts here, and the force is taken to be acting in this direction. So, it is destabilizing it. So, you can find out now the factor of safety by considering all these forces. We have to consider the moment about point O. About point O, this cylinder is trying to rotate. Resisting forces will be available from the cohesion which is acting along the periphery of the cylinder. This weight will be acting in the downward direction. So, the lever arm will be this distance, the perpendicular distance between these two lines. One line is passing through the center, another through the CG, and the earthquake force Kh into W, it is acting in this direction, in the horizontal direction. So, for this is the lever arm. So, again we are assuming phi u is equal to 0 and the forces as I discussed are the weight of the sliding mass. Number 2, horizontal inertia force kh into w, where kh is a coefficient. It is the ratio of horizontal component of earthquake acceleration and g. And third force is again the same cohesive force along the sliding surface. We will be taking the moments. So, moment of driving forces md will be equal to w into L1. L1 is the lever arm for weight and L2 is the lever arm for the force due to earthquake. So, w into L1 plus kh into w into L2. The moment of the resisting forces will be the length of the arc along which these forces are acting, and then you have to multiply them by Cu. We are assuming it is limiting case, otherwise Cm can be taken when it is a safe case, and into radius. So, that gives you the resisting moment, and the factor of safety expression is very simple. Fs is equal to the resisting moments upon the driving moments. And again we have to use the same procedure as we did last time. We have to find out the weight, we have to find out the Cg, we have to do this analysis analytically or graphically. Some standard graphical solutions are available, and in those solutions it is this factor of safety has been defined as Cu upon gamma h into m. This is the way in this form the graphical solutions are available here, where m is stability factor. It is nothing but the reciprocal of stability number. So, graphical solutions are available, and from those graphical charts, from those solutions you can find out m. Once m is available, then you can have a relationship between factor of safety, Cu, gamma and h, and you can do the any analysis, any parametric analysis. Some of them may be known to you, some of them may be unknown. You can find out the unknowns. Graphical solutions are available to get this stability factor m. Here are the solutions. On the x axis you have the coefficient kh, on y axis it is the stability factor m, and these curves, there are different curves, you can see 1, 2, 3, 4 curves are there. They are for different values of d. D is the parameter which we recently defined. The first curve you can see is for d equal to 1, then second one is for 1.5, then 2 and 4 here, and this first chart is for beta equal to 10 degree. So, similarly here now the values are not written here on y axis and x axis, they are the same, kh here, m here, and this particular value is 4, this particular value is 8 and this is 12. Similarly, the third chart, so the second chart is for beta equal to 20 degree, beta equal to 30 degree, and then you have beta equal to 40 degree, 45 degree and 50 degree. On x axis you always have kh, y axis m, and there are different curves for different d values. So, for intermediate values you can do the interpolation. Here the variation of the stability factor m is given with kh for the toe failure. The earlier cases were up to, you can see, up to beta equal to 50 degree. If the beta is more than 53, it is the toe failure which is going to take place. So, here on the x axis it is beta and on y axis it is m, and these are the curves for different kh. So, obviously, there is no parameter d for toe failure. So, for different kh values, any kh value for corresponding beta value, you can find out the m and then you can do the analysis. I will demonstrate the applicability of these graphical methods through this example. It is given here a cut slope in saturated clay makes an angle of 60 degree with the horizontal. The properties are Cu equal to 25 kPa, gamma equal to 16 kilonewton per meter cube, Kh is given now 0.25, determine maximum depth to which the cut could be made and depth of cut if desired factor of safety is 2. So, now given beta is equal to 60, Cu is this much, these are the parameters given. For critical slope, Cu will be equal to Cm, factor of safety is 1. So, Fs is equal to, the equation is Cu upon gamma h into m. So, h is equal to, h becomes Cu into m divided by gamma. So, for beta equal to 60 degree and Kh is equal to 0.25, I have previously shown you the curves, and for beta equal to 60 you can directly get value of m, and beta is more than 50 here you can see. So, it is the toe failure case. So, m is equal to 3.6. So, when you put it in this equation, you will be getting straightway 5.4 meter. This is the answer. So, this is very convenient method, very convenient tool. These graphical methods are very convenient for doing the analysis. Similarly, you can do the analysis when the factor of safety is 2. So, Fs is equal to 2, and in terms of the stability factor, it is Cu upon gamma h into m. So, h becomes equal to here. From this equation you can get h is equal to Cu into h m divided by 2 gamma. M you already know for those values, and then h you can calculate, and finally h is equal to 2.7 meter. So, these were the cases where we had clay soil only and it was completely saturated, and phi value was taken as 0. So, only Cu was applicable. Now, we are proceeding to the next case. Again we are taking the mass procedure, means we will be treating the soil mass as a whole, but now the soil is homogeneous C dash phi dash soil. So, it has both the properties now C dash as well as phi dash. The first method which we are going to discuss is friction circle method. Let me first discuss the physical concepts of this method. Whole body of the soil mass is considered simultaneously. As I told you, it is a mass procedure. So, the entire body of the soil which is trying to rotate is considered as a free body. Then trial circle is drawn as usual. Now, at the center, a circle called friction circle with radius r sin phi dash is drawn. Let me show this figure. Here it is the trial circle. We have taken the first trial, and this is the center of this circle. Now, here if I take the frictional force will be acting in this direction, the reaction will be taking in this direction, the resultant of these two will be inclined at an angle phi. This is very well known fact. What I am doing here is, let me draw a circle here, and the radius of this circle I have purposely kept as r sin phi dash. So, what happens is that if you draw a line here, at an obliquity of phi, this angle will be phi, and this line should touch this circle. The reason is very simple. We have taken the radius of the circle r sin phi dash, and this distance is r, this angle is phi dash, and this triangle is a right angle triangle. So, automatically this becomes r sin phi dash. So, here if a line at an angle phi dash with normal to the surface is drawn, it should touch the circle tangentially. Mathematically, we can very easily prove it. This circle is called as friction circle. Now, the forces which we are considering: weight W of the mass above the trial circle, that is the first force. Secondly, the resultant boundary neutral forces. There will be the force due to pore water pressure. So, the resultant of all those forces, this is the resultant U, resultant boundary neutral force U. Thirdly, resultant intergranular force P acting on the boundary at the frictional at the boundary of the circle, and resultant cohesive force. So, we are treating these forces separately. Cohesion we are taking separately, and intergranular force, here friction and the reaction we will be taking combinedly. Let us discuss these forces one by one. Actuating forces. So, the actuating forces, the forces which are trying to destabilize, is weight W. So, weight W, let us say this is the CG of this wedge, cylindrical wedge, and weight W is acting in the downward direction. Second is force U, and U is the water pressure. It has to act normal to the surface. So, necessarily this vector U will be passing through the center of the circle, trial circle. So, force U acts along the radial vector. So, we have to find out these two forces from the geometry as well as from the flow conditions, and then let us say the resultant of W and U is Q. So, W is acting here in this direction, downward direction, U is acting in radial direction, and here it is the resultant Q. Now, come to the cohesive forces. This is the trial circle, and let us divide. If I take very small segments all along this trial circle, all along this arc. So, this is small segment, another small segment, third small segment, and so on. So, let us say the cohesion along these small segments are C1, C2, C3, and so on. If I plot these cohesions separately here and then plot this polygon, so C1 will be here, C2 is here, C3 is here, and so on, and then you can find out their resultant and also the magnitude of this resultant, direction as well as magnitude. So, if you compare this figure and this figure, the resultant should be equal to, in magnitude it should be equal to this length, and its direction will be in this direction. So, the resultant of these cohesive forces will be equal in magnitude, and it will be parallel to this line AB. AB is the chord here. So, let us say the length of the arc is LA, this is the length of the arc, and this is the chord, and you know that length of arc is always more than length of chord. Length of chord is, let us say, LC. Dividing the arc into smaller segments and then taking the mobilized cohesive forces on these segments as C1, C2 and Cn as I discussed, Resultant of all these small cohesive forces is A dash B dash. It is shown here. A dash is this point, B dash is this point. So, this is the resultant, where A dash B dash is parallel and equal to A B. This is necessarily it will be parallel and equal to this chord A B. The resultant cohesive forces, therefore, the resultant of all these cohesive forces C will be equal to Cm dash. Cm dash is the mobilized cohesion in effective terms into length of chord, because its magnitude is available with us. So, the resultant cohesive force will be equal to Cm dash into Lc, where Cm dash is nothing but C dash upon factor of safety against cohesion, C dash upon Fc. Now, we know the magnitude of the cohesive force, we know its direction, but still we do not know where it is acting. The line of action of C is obtained by moment consideration. The moment of this force will be equal to Cm dash. We are taking moment about the point O, because this cylindrical surface, cylindrical volume is trying to rotate. So, moment of this cohesive force, the resultant force will be equal to Cm dash into Lc, that is the magnitude, and let us say La is the lever arm or the moment arm from the center of the circle. So, from A, La is the distance where this C is acting. Now, this moment should be equal to the moment of small cohesive components which we took last time. So, if I take these components C1, C2, C3 and O and so on up to Cn, then all these forces are acting perpendicular to the radial vector and their lever arm will be equal to the radius of this particular trial circle. So, the moments of small cohesive forces will be equal to Cm dash into La. What I have done here is total arc length. If you take them separately, so it will be Cm dash into L1. Let us say L1 is this small length, then Cm dash into L2 and so on. So, this complete length is La. So, when we sum up, so it will be the total moment, the resistive moment of the cohesive forces will be Cm dash into this length of arc into radius. And when it is in equilibrium, these two values, they have to be equal. We have to find out C here. So, by equating these two moments Cm dash into Lc into small la into Cm dash capital La into r, when you equate it, Cm dash will cancel and you will be getting the lever arm of the force C will be equal to capital R into La upon Lc, where La is the length of arc. This is the length of arc, Lc is length of chord, and you know length of arc is always more than length of chord. So, La should be higher than R. So, La is higher than R. So, somewhere here it is acting. So, you can find out the line of action of the cohesive forces. It will be somewhere beyond this radius. Now, let us come to the resultant of intergranular forces. Let P1, P2, Pn, these are the effective intergranular forces on small segments. So, these are very small segments we have taken, and effective intergranular forces, the frictional component, this is P1 here, P2 here, P3 here and so on. Friction circle is drawn with radius r into sine of phi m dash. Here phi m dash is the mobilized angle. Let us say the slope is safe and the mobilized shear the angle, friction angle is phi m dash. So, the radius will be r into sine of phi m dash, where tan of phi m dash is equal to tan of phi dash divided by f phi. So, this is the factor of safety against friction, and factor of safety against friction is defined as tan phi dash divided by tan phi m dash. So, here tan phi m dash will be equal to tan phi dash upon f of phi. So, now P1, P2 are tangent to friction circle that I discussed, but the resultant of these smaller forces will miss the tangent by tangency by a small amount. So, here I have shown it. If you draw the small component, then the resultant, that intergranular force, will be tangent to this smaller friction circle. But when you take all these components, when you take their resultant, it has been found that their resultant will miss the tangency by a small amount here. Let the resultant P of all the forces is tangent to a friction circle having radius k into r into sine of phi m dash. So, let us say there is a factor k which we have to multiply, so that we get a circle modified, I can call it, you can call it modified friction circle, this one, the little bit larger one, so that this resultant passes through the is tangentially touches this circle. So, the inner circle is the original friction circle, the radius is r sine phi m dash, and outer circle is little bit bigger, radius is k times the radius of the previous circle, and this value of k you can find out from the charts, it is available. This is the relationship between the k and central angle alpha. So, on x axis you have central angle alpha. For the particular case which we have taken, for the particular trial circle, this alpha you can find out, and once that alpha is known, then you can find out the value of k. So, here on x axis you have angle alpha, y axis you have coefficient k, and you can see there are two charts, two curves, one is for uniform stress distribution and second is for sinusoidal stress distribution. So, it depends on what kind of this stress distribution has been assumed. From this chart one can find out the value of coefficient k. So, you can see it is varying from 1.00 and up to 1.20. So, the radius will be 1 times to 1.2 times the radius of the original friction circle. So, using this chart you can find out the value of k. Now, considering all the three forces P, Q and C, the force P must pass through the line of intersection of the vectors Q and C. This is the condition which should be satisfied. So, we know now the P direction of P is available with us. This we can draw this modified friction circle. This direction is available with us. This line of action of C is also available with us, and also P should be tangential to the modified friction circle drawn with the radius k r sine phi m dash. So, as per this diagram, this is the modified circle, friction circle, P should be tangential to this, and then for the limit equilibrium case, this particular force polygon should be satisfied. So, you can find out the unknowns. So, this particular force polygon, this is Q, this is C and P, this can be constructed. For determining the factor of safety, so these were the basic concepts. For determining the factor of safety, what we have to do is we start with a reasonable value of phi m dash. We use any reasonable value and then draw line of action of C. So, this is the line of action of C which we have drawn. This is the slope. We have calculated the how far it is from this radius, from this center, and line of action has been drawn. Draw first circle with radius k r sin phi m dash and draw tangent to circle and get point D. So, this is the first circle, first trial circle which we have drawn. This is the modified circle, friction circle. Draw a tangent to it. So, that gives you the direction of P and get this point of intersection D. Now, plot Q, the resultant of W and U. So, here now plot, this is the force Q which we have already calculated. Then complete this polygon, draw a line parallel to C. So, this force polygon gives you the force P, it gives you the force C, and you can find out you can find out C and P using this force polygon. So, get force P1 by completing the force polygon and then get mobilized cohesion Cm1 dash into Lc. This is the capital C, the cohesion for this first trial, for the first circle, and once this is available, then you can get Cm1 dash, the mobilized cohesion for the first circle. So, get Fc is equal to, once this Cm1 dash is available, then you can get factor of safety against cohesion. And also for the phi value which we have assumed here, for the phi m value which we have assumed here, we can get F phi. So, friends, today we have discussed the finite slopes, and we have concluded the slopes in saturated clays. We also considered the earthquake forces, and then we have started discussions on the C dash phi dash soils, and we have started one method, friction circle method, and next lecture we shall continue with the same method. Thank you.
Thank you.